Hey Dave, how's it going?
Good. How are you, Stephanie? Can you hear me okay?
Oh, hang on. Let me get the rest of the thing set up. Just give me
Okay.
1 minute. Hey Dave, everything should hopefully be working now. Can you hear me?
Yes. Can you hear me?
Yes, perfect. And we can see you. Do you want to try sharing your screens?
Yes. Sure. How's that?
It's still thinking. Give me 1 sec. Yes, looks perfect.
Okay.
All right, easy peasy. So how are you doing?
Good. How are you?
Not too bad. It's good to see you again.
Yeah, it's been a while. I think since we
Absolutely.
were out here in Boise.
Yeah, absolutely. So what's new with you?
Um, well, I'm not sure. Since we last talked, this year I got the P case in January.
Congratulations. That's awesome. That's a
Yeah.
huge honor. Amazing.
Yeah. Get to join the club you're in. Um,
Yes.
but yeah,
Fantastic.
it was pretty funny because I'm obviously not really career anymore, but those things are so far
They're so
behind.
behind, yeah. Because that must have been from what, like many years ago.
2017 was when I got
Yeah.
nominated. Yeah.
Holy crap. That is a very long time ago.
Yeah. Yeah. So that's new. And then got promoted to full this past year. So
Congratulations. Also awesome.
yeah, and our MOCVD is up and running. So I'll show some of those results. So that's cool.
Excellent. Yeah, I'm looking forward to it.
Yeah.
Mm.
So what's new with you?
What's new with me? Yeah, I don't know. Finally got all settled in at Penn State, I think.
Yeah.
MBEs are actually, working for now, for the moment.
Knock on wood.
Yeah, right, exactly. So, yeah, I don't know. I'm the program chair for the American Vacuum Society symposium this fall, so that's coming up in a couple weeks. So that's been absorbing a lot of my focus.
Yeah. So I'll see you in Charlotte probably.
Oh, good, you're coming. Excellent. I know I'd seen you on the thing, but then we've had a lot of people changing their plans recently, so I'm glad that you will still be there.
Yeah. It's actually a multi-city trip. So I'll be traveling for about 3 weeks.
Oh
Which
my gosh, where all are you going?
Chicago, Charlotte, Sydney, and Melbourne.
Oh my gosh, that's a lot of travel.
Yeah. Yeah. That's cool. It'll be fun.
Yeah, I hope so. Yeah. So are you not teaching this fall then, or you just have to
No.
deal with 3 weeks off? Okay. Yeah.
Yeah.
That's nice.
Yeah. Fortunate.
Absolutely. Yeah, so we usually give people a little time to, get their food and get settled. So we'll probably start a few minutes after noon, if that's okay
Okay.
with you.
Cool. And I have a ton of slides. I'll try to go through them quick, but I don't know.
Okay. Yeah, we usually try to finish up around 1 because people have to get off to class and whatnot.
Okay. Yeah, I can definitely hit that. So,
Fantastic. And this is recorded,
okay.
so we usually post them. Is that okay with you, or would you rather not?
Oh, yeah, no, that's fine. I think most of everything here is published, so no problem.
Great. Fantastic.
So you're taking more of a leadership role in 2DCC?
Yeah, so if the transition proposal gets approved, I'll be the associate director
Oh, excellent.
for the transition period, and then potentially maybe director eventually if Joan decides she doesn't want to do it anymore.
Yeah. It's a lot of work, I imagine.
I think it is. Yeah, right now I'm just the director for education and training programs, or
Oh,
education training and outreach. I don't remember exactly what it's called anymore,
okay.
but I organize webinars, and we just put in, I'm the PI on an RU proposal we just put in for an RU site for 2DCC. So we'll see what happens with that.
I'll wish you good luck, but don't take it the wrong way, because those things are very difficult to run. I don't wish
Yes.
you a tough time, but I wish you success.
Yes. Thank you. So yeah, we'll see what happens. It's actually, it's an interesting topic. It's AI/ML for 2D materials, synthesis,
Oh,
characterization, and modeling. So I think it'd be really cool if it got funded, but
yeah.
you never know, like what the reviewers are going to say or what anybody is going to think. So yeah, so we'll see.
Yeah. You guys are doing great work out there.
Yeah, thank you. 2DCC, it's a really nice resource to have, I think. So here's hoping that the transition period will be funded and we can keep doing what we're doing. But we'll see.
Yeah, it's a neat program. I mean, we wouldn't be doing MOCVD without it, right? Because
Yeah, right.
very
Yeah.
difficult to get that kind of training elsewhere.
Yeah, I mean, it's not often that we just let people come to our labs and work with us for extended periods of time and learn everything we know and then go away and take that back. So
Yeah.
yeah, it's a very unusual kind of program.
Go build the capabilities at your place now, right?
Yeah, right,
So you
exactly.
can
So,
compete.
yeah, so hopefully NSF recognizes this and will continue to support us. So
Yeah.
we go down in 2 weeks, I think. So.
Okay.
Yeah, my September is crazy. I'm giving a talk at Carnegie Mellon, then I have to go to NSF for this thing, then we have AVS, and then I have another seminar. So I'm just,
Wow.
the rest of the semester is fine. It's just September is like a gigantic mess.
Yeah. September here is archery season for those that hunt big game. So it's always quiet here, but for different reasons.
Right. Yeah, that makes sense. All right, we're getting a few people here. Yeah, I would say we'll give it maybe another 3 or 4 minutes. Make sure everybody can get settled. Make sure all the online people can log on. It's always the tricky part with this, having some in-person people and some people online and trying to make sure that we can get everybody.
Yeah.
Everybody here. Yeah, so how is your MOCVD going?
Good. So we qualified in February.
Nice.
It was about a 4-year install, 3 to 4 years from purchase, like going through all the state board approval process, purchase order, construction, qualifications, right? But we ran WS2, MOS2, HBN, graphene during our qual, and now we're focused on WS2 synthesis.
Nice. That's awesome.
Yeah, so it's exciting.
Yeah.
Very expensive.
I was just gonna say, how was it to get all the facilities stuff ready to handle the gases and the power?
That was a piece of cake. We hired an engineering firm, and they did all the drawings. We ran them through Extron, right? Make sure everybody was on the same page. And then here in Boise, because we have Micron, there's a company called Critical Systems, and they do this kind of stuff all the time.
Right.
We purchased from them all the gas safety cabinets, scrubber, everything. So they came integrated with the building alarm systems, did all the training for the staff. At one point, we had, I want to say, about 12 fire trucks here because it's like 4 different firehouses that have to respond to Boise State University in emergency. And so we brought all the firemen here to train them on like what the dangers could be of H2S, H2SE leak, and that kind of stuff.
Wow. Well, I'm glad the facilities part went smoothly. That's often like the hardest part of any instrument install. So I'm glad at least that went well.
Yeah, it was cool. It's pretty exciting. It's definitely it's the first MOCVD at a university in Idaho, right? So.
Yeah. I mean, I think MOCVDs at universities are not so common. Oh, hey, Joan, we're just talking about MOCVD.
Oh, hello. Hey, David.
Hi, good to see you.
Yeah, good to see you. Thanks for giving this webinar.
Yeah, no, I appreciate it. I was just telling Stephanie, 2DCC has been very impactful on my career and capabilities here. And so happy to give a seminar and show some of the results we're getting.
Yeah, nice. That's our job.
Yeah. Yeah.
Yeah, so we'll start in about another minute or two. Just let all the in-person people get their pizza, take their seats, and then we'll get started shortly.
Cool. Yeah, I'm surprised if we haven't run into each other at a conference this year, Joan.
Yeah. Did you go to the TMD workshop, the one in Cambridge?
Yes, yeah. So
Okay.
I saw Andrew there.
Yeah, I wasn't able to make it, but I heard that was a great meeting.
Yeah, it was awesome. Yeah, Andrew gave a great talk, and it was highlighted as a model for all the grad students in the audience.
All right, well, it looks like people are more or less settled here. We have online people, so we can go ahead and get started. So our speaker today is Professor David Estrada. So he is a professor in the Material Science and Engineering Department at Boise State University and a longtime colleague of mine. So Dave and I were postdocs together at the University of Illinois at Urbana-Champaign way back in the day. So now he is a variety of things. He's the site director of the National Science Foundation Center for Atomically Thin Multifunctional Coatings. And he has won many awards, including just recently the PK's Award. And so we are delighted to have Dave here to tell us about his work in 2D materials. So take it away whenever you're ready.
Great. Thanks, Stephanie. Thanks, Joan. It's a pleasure to be here with this audience for the 2D Crystal Consortium. You've probably heard I was just saying it's been very impactful on my career and my students and bringing new capabilities to the state of Idaho. So today it's my pleasure to talk to you about some of the work we're doing with 2D materials and 2D and layered materials for energy, water, and healthcare. As Professor Law says, I'm a professor in material science engineering at Boise State, but my background is really electrical engineering. This has been all my training in semiconductor device physics. I think Penn State knows Boise State pretty well, probably from the college football playoff last year. So maybe if we can get you guys out here on the blue turf, we'll have a different outcome this year or in the future. But if you're not familiar with Boise State, we are located in the southwest corner of Idaho, here in the capital city of Boise. Most people do know that Micron has a presence in Boise. It's where their research and development headquarters is located. And so, Micron's been a big beneficiary for the university. And there's a large semiconductor ecosystem surrounding Micron in terms of equipment suppliers and just the support for the facility. Micron recently announced 2 fabrication facilities are being built here. So you can kind of see the construction is ongoing. I believe I heard it's currently the largest construction project in the United States. So they're a fab for 3D NAND and high bandwidth memory here in Boise. So this year they expanded this 15 billion to 25 billion for those 2 fabrication facilities, with also plans for an advanced packaging facility, which the site hasn't been announced. So Boise State is a member of the Midwest Microelectronics Consortium, NextFlex Manufacturing USA Institute. We have strong partnerships with Eastern Idaho in the Idaho National Lab, which is the Department of Energy's nuclear energy office laboratory, right? So they do the peaceful side of nuclear for the nation. So that's a little bit about us. My group here at Boise State is known as the Advanced Nanomaterials and Manufacturing Laboratory. And we really focus on trying to understand new materials, nanomaterials, and their fundamental electrical, thermal, transport properties, chemical properties, right? And how we can then use that information and apply them in these different sectors, right? So healthcare, energy, and the environment. You can see a lot of the different projects here. So today I'll highlight kind of one project in each area. But one thing we try to do is that we try to not only do the fundamental research in the lab from the TRL 1 to kind of 3 level that is pretty common for bench type research. We try to use tools that can translate to industry so that we can help bridge that TRL 4 to 6 gap or that valley of death as things get commercialized, right? We do a lot of work in both top down and bottom up. Well, new to us is the bottom up synthesis of 2D materials, but we've done a lot of work in top down synthesis of 2D for formulations for aerosol jet, inkjet, plasma jet, different materials jetting platforms that are compatible with fabrication of different devices in industry. So I'll talk a little bit about that today in our work in printed electronics, how we got started there. And towards the end, I'll give a highlight on recent results off our new Actron MOCVD for 2D materials. So I start with this slide, which kind of motivates a lot of the work that have been doing in printed electronics, which was really impactful on getting me started in printed electronics. It was a collaboration with NASA Ames Research Center and Marshall Space Flight Center, and getting integrated into their in-space manufacturing program. Right. So if you're not familiar with in-space manufacturing, a lot of the motivation for it comes from the need to resupply the International Space Station, as well as have kind of these forward bases for manufacturing to supply the Artemis mission on the return to Mars, right? So NASA sends about 3,000 kilograms of spare parts to the ISS annually. This is about $22,000 per kilogram to ship that up to ISS, and I think it's roughly $70 million per year. ISS is only 400 kilometers away from Earth, right? That's low Earth orbit. But the Artemis mission intends to take us back to the lunar surface and eventually to Mars, right? And so you can imagine that if we are resupplying the mission, the crewed missions for these application or for this mission, the cost is going to grow astronomically, and it won't be sustainable, right? On ISS, about 30% of the failures are related to electronics, right? And so these are these PCB boards. And so when they fail, they just get trashed, they put in the spare, and then they ship from Earth to replace the spare, right? And so there's a big motivation to be able to manufacture replacements on station, to send the digital design, whether it's a structural component or an electronic component. And so this has led to kind of on-demand manufacturing of metals, on-demand manufacturing of electronics, as well as recycling and reuse of materials programs under this in-space manufacturing initiative. We plugged in with the on-demand manufacturing of electronics program, really to develop print electronic sensors and devices on station, and help NASA kind of down select different printers, as well as develop new materials for printers for this manufacturing paradigm. So you can see ODME focuses on development of electronic inks. Originally, we were screening different material printing modalities, right? So things like the Inscript extrusion-based printer, the Space Foundry plasma jet printer. We've helped develop laser sintering processes for printed electronics, and kind of we've been working towards a demo that can be fully manufactured in space, known as AstroSense, which is this next generation flexible wearable device to monitor true health, right, through kind of sweat monitoring, temperature, and these sorts of things. And so that concept is captured here, where each of these layers represents a different functionality to that sensor, including your power, the electrochemical sensing, and different. And so this demonstration was to occur in 2025. Things have been a bit chaotic in terms of programs and funding, so that's been pushed back a little bit. But the initial demonstration should be on Fab Lab and ISS soon, as a precursor to Gateway, which will be kind of the lunar ISS, and then eventually to the lunar surface. So the need here really has been evaluate different printers and develop new materials, right? So in terms of materials jetting platforms, we've worked with several different print modalities. Inkjet is by far one of the most technologically mature materials printers. It works on a drop on demand, where you basically apply electrical pulse to a piezoelectric head. That pulse deforms the print head in a way that you can overcome the surface tension of ink. The nanoparticle drops onto the substrate, and then kind of translate to the substrate to print your device. The aerosol jet printer is kind of a newer technology. In this case, you have your ink sitting in a glass vial. You put some energy through megasonication. That creates an aerosol right above. Your gas will come in, pick up those droplets, take it to the print head where a second gas comes in. This is the sheet gas, and focuses the beam. And so you can actually get a large laminar flow distance, about 3 to 5 millimeters or so. Gives you a good standoff, and so you can actually print conformally over 3D substrates with this. You get better resolution here. Inkjet's about 50 microns in lateral resolution. Aerosol jet, you can get down to about 10 microns. Plasma jet works a lot like aerosol jet. Ultrasonic or megasonic atomizer, but at the print head, you end up going through a cold atmospheric plasma, which allows you to do plasma chemistry on your particles as they go through, helps dry the solvent, and the plasma can actually clean the substrate, charge the substrate, and improve adhesion as well. And electrochemical hydrodynamic jet, we've worked a little bit with this, but I think some of the leaders in this are at Michigan and Illinois. But it works a lot like inkjet, where you have kind of your print head, but you apply a high electric field between the nozzle and the substrate. That results in the formation of a cooling film, which can print down into the tens of nanometer resolution. So you can kind of look at the spider plots to look and compare quickly the different metrics of these printers. Viscosity is a big one that we have to tune. Things like aerosol jet, you can have higher viscosity than E-jet, right? Than inkjet. But particle size may be limited in inkjet. Speed is much greater, right? So lots of different pros and cons for each printer. And so it really depends on your application, which one you're going to pick. I will say that for ODME, plasma jet has been proven in microgravity environments, whereas the others I don't think have really. I think inkjet as well has been shown to work in microgravity. All right, so what does it take to make an ink for these platforms, right? So really, we have to pick a new material. We have to synthesize, and I should say we work on nanoparticle-based inks largely, right? And so you then have to synthesize your nanoparticles, and there's a couple ways to do that. You can use a top-down physical milling kind of approach, or you can do a chemical synthesis from different reactants and create nanoparticles through control of that reaction, right, through the kinetics of that reaction. And so once you have your particles, you're either going to end up with some type of powder, right? Or you'll end up with your particles in some chemicals or solution that may or may not be compatible with your printer, right? Either way, you then have to select your printer and then formulate the ink in such a way that it's going to jet in these platforms and that the chemicals are compatible with the parts of your printer and aren't going to corrode your printer, right? So this involves maybe adding different binders, co-solvent systems, understanding the rheological properties and the stability of your dispersion. And so you characterize that through things like dynamic light scattering, surface tension measurements, contact angle tells you how it's going to interact with your substrate, right? Viscosity measurements, all this. And then here at Boise State, we have a lot of these printers, so we can quickly go test our inks on the different platforms and reformulate as necessary to get a jettable ink. We're really targeting, and what we found works well for both inkjet, aerosol jet, and plasma jet, is that we tried to tune the Onsarge number in relation to the Reynolds number of the printer, right? And so this includes the viscosity of your ink, the surface tension, the density, and the nozzle diameter. And in Reynolds, we also take account like the gas density, the cross-sectional area of the nozzle, and the viscosity and the gas flows. What we're looking for is trying to get our ink within this printable window of Onsarge versus Reynolds. And so we want to be within this range here, right, of 1 and an hour. And that gives us good printability. This is a very famous plot for inkjet in particular. For aerosol, we add a high boiling point solvent as well and try to stay in this window. And that just helps keep the line well defined after you do your print. Right? So we can take our formulations in and outside that window. So you can see here a lot of the different inks that we've been able to formulate, not just 2D material inks like the TMDs, MXenes, or layer thermoelectrics, but we can also do different nanoparticle inks like nickel, gold, platinum, molybdenum, which allows us to do some work function engineering or high temperature applications when we put those in as compounds. So I don't think for this group I have to motivate 2D materials, just to say that these are the different 2D materials we're able to synthesize here at Boise State. We've done a lot of work with black phosphorus, the TMDs. We've been making tellurine recently, hexagonal nitride as insulator. So basically, we have all the components for electronics here, from semiconductors, insulators, and metals. So that's one of the advantages to developing these inks for printed electronics applications. Right? Well, I'll talk a little bit about one of the applications we've been targeting for energy storage and energy harvesting that NASA's been interested in. And really, one of them has been, can we print supercapacitors for energy storage, which could then power things like wearable sensors, right? So those supercapacitors, right, their efficiency is really determined by their active electrode material, the electrolyte, the separator, the current collectors, and all these components can really determine the performance of your supercapacitor, right? There's a couple of different configurations that are easy to print. You can do a stacked configuration where your current collector is printed, then you print your active material, you put down your electrolyte, your next active material, and then the next current collector, right? But we've been focused on this interdigitated planar configuration where we print these IDE structures, coat them with our active material, and then just dip them in our electrolytes to characterize their energy storage performance. And supercapacitors are interesting because they really bridge the power density and energy density of regular capacitors and batteries. So this is good for applications where you need a fast discharge or quick bursts of power. And they're quite common in automotive, aerospace, energy, and medical applications where you might need those quick bursts. For this application, the 2D material of choice that we decided to look at was done in collaboration with Yuri Gogolsky at Drexel University, and we're looking at MXenes as the active material. MXenes, they come from the max phase ceramics, where you have the formula M+1, M here is a really transition metal. A elements are typically shown here. Silicon, aluminum, gallium seem to be some of the more common ones. And then X is typically a carbon or a nitrogen or a combination of the two. So, you can see some of the different types of MXenes that have been realized from the 2-1 ratio, 3-2, 4-3, and more recently the 5-4 has been synthesized. And you can see you can get different solid solution in the transition metal, different layer ordering. So that like a lot of the 2D family, right? A lot of interesting things to explore within the MXene family. Structure and how that affects their properties for these different applications. It shows here too, after you etch away the A element in these in these max phase ceramics, you get the MXene phase, right? You get the transition metal and the X, the carbon or nitrogen, and then in that etch process, we also develop a surface functional group, which tends to be hydroxyl, oxygen, chlorine, of the transition. In our group, we went to Drexel. We learned from Yuri's team how to synthesize these, and we've been applying the biosynthesis method, where we do an in situ reaction to generate HF by mixing acid and chloride, and this facilitates the etching of the aluminum layer from the type 3 aluminum carbide max phase. Do that etching just on a hot plate over time. We neutralize that, wash it multiple steps, and then we pour the MXene clay, let it dry, and then we get these MXene papers, which we can then first into our post-solvent systems for the platform of choice. So we've been targeting aerosol jet printing for now with the MXenes. And aerosol jet printing, or particle size, has to be about 200 to 500 nanometers in lateral dimension, right? So than that, you risk clogging your nozzle. Titanium does oxidize fairly easily, especially when you use particle size. The Ti3C2 oxidizes quite easily. Some of the other MXenes, like niobium, really oxidize quite a bit. What we've done is we follow some of the work from Josh Wood and Mark Herslam, where we actually do our synthesis using deoxygenated solvents, and we seal everything in an argon glove box before we do probe tip sonication to reduce the particle. Here, where we have our solution in ice, but this probe tip is actually a PDMS system that will seal under argon, and then we take it out and connect it to the probe tip sonicator to do the particle size reduction. We measure that with TLS. You can see we're down in that 500 nanometer range, 500, 600, which works well for aerosol jet. And you can see we use a co-solvent system. I think it's ethanol, water, and ethylene glycol for this work. So we did the ink characterization. You can see the shear stress versus shear rate. With a 4 centipoise. That works really well for the aerosol jet ultrasonic atomizer. And we have a nice contact angle on our printed gold, which we're using. Here's an example of some of the prints we can achieve with this ink on our Optomec 200. So this is just kind of a large area image. This is 2mm scale bar showing with the visual design, you can print arbitrary patterns, high resolution. So as we scale in or zoom in, right, you can see some of the finer features. We were able to achieve around 45 micron line width for these prints. So that's pretty good for printed 2D materials, right? Push down to about 10 microns, but you get a lot of overspray. Here's an example where we printed on an aluminum tube. This is a 5mm bar, so about a 10mm diameter. So we can print the pattern directly on 3D surface. We did do some TLM measurements and show that as we increase the pass number, print pass, and then we go over it again, 2 and 3. Thickness of the MXene layer and reduce the resistance. This is just a cross-sectional SEM showing after we dry out the solvents, we do anneal these at about 300 Celsius. But we do end up with quite a bit of porosity, about 27% porosity in the print. Other like compaction steps or something to try to reduce the porosity. This is a pretty common capacitor. We actually use a gold current collector, and for that, developed our own gold ink. Those details are so we use a gold nanoparticle ink. We print our energy shade electrodes. We anneal that at 350 to remove over and use our MXene developed ink. And so this was recently published in June. All the details of this printed supercapacitor and ink development are in this small methods paper. After our print, we decided to characterize we characterize the supercapacitor performance. We're saying 1, 2, 3 layers, right? Print passes, but you can also think of this in terms of thickness. So after 2 microns, I'll just say that the layers laminate. That was about the thickest layer we could print. So here's just a comparison of the CV curve, right? And you can see that the capacitance increases, right, as we increase the thickness of the layer. You can see that as well in the GCD curves, the converge curve. And when we calculate the capacitance and normalize by the area of the electrode, you can see we control the limit of the printer to get some higher resolution. And so we did do some cycling as well. So we about 10,000 GTD cycles. We're retaining about 86% of the capacity. And drop is due to just a little bit of increase. I should say we're using sodium perchlorate as our electrolyte for these curves, but we also did do a aqueous gel electrolyte as well. This curve tells us the storage mechanism for this MXene. We're not the first to print supercapacitors. I think we're one of the better ones for aerosol jet printing. You can see capacitance per unit area versus current density compared to other supercapacitors. You might have Nicolesi's work at Trinity College Dublin, and you can see that we're outperforming those prints. Electric capacitors as well. Against other materials and other printed supercapacitors, we're getting very good. It's just some of the highlights of the paper. If you're interested in this, I'd encourage you to go read a lot of the details in that work. That's the energy storage side. Turns out MXenes can actually help enhance energy harvesting as well. And we turn to triboelectric nanogenerators, which is basically a way to convert mechanical energy to electrical energy through contract electrification, right? comes in contact with the electron acceptor. The charge has to redistribute when these two come into contact, and eventually it'll come to equilibrium. And as you take them out of contact, that charge will redistribute again. That gives you these characteristics of voltage versus time curve. For this, we used PVBVA. It's a fairly newer polymer. PVA has been around for almost a decade, right, or a century, but nation of the harvesting devices. And it is sustainable. You notice that there's no long chain fluoropolymers, fluorocarbons in this polymer. Tank devices use so to make this device, we started with just our PVBVA dissolved in ethanol at about 7 weight percent, and then we could add MXenes at different concentration, just through shear mixing. That creates a thick viscous paste that we can use an extrusion printer for. We just use pneumatic, just use compressed dry air to push the syringe, and we can print arbitrary shapes. Metal printer for this. It's a single electric device where we can print our polymer composite directly on aluminum foil or a printed silver electrode. In
the audio when you're listening to it online.
So here's kind of some of the tank performance versus concentration of the MXenes. We were able to get up to about 5.5 weight percent of MXene in the PVBVA before they crashed out. Right?
I don't see comments like in this.
Solubility limit and the voltage that we're able to achieve with the additional of the MXenes is about 200.
Hey, Dave.
Yeah.
For the people online, apparently something is very wrong with the sound. I'm not totally sure what to do about that. Yeah.
I think if maybe mute your room.
Yeah, sure. I can try to mute us and see if that.
That worked. Yeah, that it's coming just the noise on your microphone. Yeah, so thank you. That was I wasn't quite sure where that was coming from. Thanks, Stephanie and Joan. So yeah, we're trying to understand that solubility limit, the fundamental mechanism of that. But even within this range, you can see we're able to get over 2x increase in the voltage by the addition of MXenes to PVBVA, as well as in the current as well. And so this gives us a max power density of about 750 milliwatts per meter squared at a load resistance of about 10 mega ohms, which is quite good compared to other tank devices that are not using the fluoropolymers, right? And so here, just an example of we're able to put this tank device through a rectifier circuit, charge a capacitor, and illuminate, I think in this case, 34 LEDs with that conversion of that mechanical energy. Okay, so I know I'm probably, I tend to go long on these things, so I'll try to speed up. But I'm going to shift from the energy storage and harvesting and kind of show some of the work we're doing in water and healthcare next, right? So in water, one of our motivations here, this is the work we did with Idaho National Lab, has been to how to treat agricultural waste streams, right? And in Idaho, agriculture is, of course, one of the major parts of our economy. And dairy, we're actually the largest, the third largest dairy producer in the nation now, with I think we have over 650,000 cows, milk cows across the state. A large portion of that runs along the Snake River Basin, which spans western Idaho and southwest and southeastern Idaho, right? And this aquifer is about the size of Lake Erie, right? And it really supplies a lot of the drinking water for the population in the state here. So when we have these large dairies, the runoffs, especially in these the liners of these dairy lagoons, if they break, you risk putting a lot of phosphates and nitrates into the groundwater, right? And that can be detrimental to the health of the aquifer, and if it gets into the drinking water, can also have health risks for certain segments of the population, right? And so we decided to see if we can use different approaches and materials innovation and nanotechnology to help address removing contaminants from such waste streams, right? Such water waste streams. So, I put this up. This is kind of an older paper now, but nanotechnology, I think, could have a big impact in water remediation. And, this was captured by Alvarez, where, using nanotechnology for removal of heavy metals, scale forming ions and phthalates, anions, those nitrates, fluorides, pesticides, right, and salts. Nanotechnology can have a big impact here through integration with things like selective absorbance, media filtration, right? Catalyst, membrane development for CDI cells and things of that nature, right? And so we're kind of mixing these new 2D materials with existing CDI technologies to address this water remediation issue. Our approach was to use flow electrode capacitive deionization. And so this is a lot like a regular CDI cell where you have kind of your anode and cathode. You have kind of a carbon cloth here just to get good electrical contact to those collectors. And then these are separated from your waste stream through ion selective membranes, right? And then your waste stream goes to the center of the cell. And so as you apply a bias, you can pull the pollutant ions out of the waste stream across the selective membranes, and then they either attach to a membrane or they can go into your electrode system, right? And the difference between CDI and flow electrode CDI is that instead of having a stationary membrane to collect those ions, we actually use a slurry that is pneumatically pumped through the serpentine channel. And those ions, when they come out of the waste stream, will go into that slurry and get collected in that flowing electrode, which can go out of the cell. You reverse the bias at that point and remove the pollutants from your flow electrode, and then you can regenerate and go back into the cell to pull more pollutants, right? We have kind of a closed system, which gives us this characteristic curve. We have an initial conductivity for our waste stream with the ions. As we pull them out, that conductivity will drop, and then we will reverse it still in the cell and put the ions back in, recover the conductivity, and drop it again, right? And so we're looking at the number of cycles we can achieve with these new materials and the ratio of the initial conductivity and final conductivity, which can tell us things about ion absorption capacity, energy consumption, and things of this nature, right? So it's a pretty conceptually simple design. In theory, it can run ad infinitum operation. It's modular. You can put these in parallel to treat more water, right? You can actually use it to recover, not just purify water, but you could maybe recover critical minerals or materials, critical ions out of that waste stream. Ammonia is one of those that may be harder to synthesize than just recycle, right? So you kind of see our conditions here for the batch mode operation. We're using an ammonia chloride to simulate the ammonia that might be present in these agricultural waste streams. So this just shows the stability of our electrodes. In this case, we're still working with the Ti3C2 MXenes, and we're comparing to activated carbon. And so we did particle size analysis. Typically in the flow electrode CDI community, people have been using 10 weight percent activated carbon as their flowing electrodes, but these are microscale. They can clog that serpentine channel quite easily. Our MXenes are much smaller in the hundreds of nanometer regime. Our viscosity is on the order of that of DI water, because it's largely DI water. We're only using 1 weight percent MXenes in this case. And the viscosity is a little higher on the activated carbon, but really it's the zeta potential that you can see here. We have a much larger or smaller, I guess, more negative zeta potential with the MXenes, which makes them more stable in the DI water that we're using to flow in the electrode. And this is over 4 weeks. I don't have the time here, but over 4 weeks, you can see the activated carbons crashing out, and ours are still quite stable. So here, some of the results for this work. This was published a couple of years ago in Nature Partner Journal Clean Water. But you can immediately see that with the Ti3C2 MXene, we look at that conductivity cycles, we're able to achieve about 3 times the number of cycles as compared to activated carbon over the same time period, right? And when we use this conductivity ratio to back out the ion absorption capacity, we're actually able to achieve about 100x improvement in the ion absorption capacity with the MXenes. And that comes from the layered structure, largely from the layered structure of the MXene. And so we were able to remove the anode and analyte and catholyte at different parts, right? At the minimum here, and then do X-ray diffraction analysis and show the expansion of the D spacing parameter, the 002 peak, right? And so that tells us that the ammonia ions are being captured between the layers, expanding that lattice, and it comes out to about 15 angstroms, which is about 4 ammonia ions if you were to stack them on top of each other. So that helps explain why we're able to get much larger ion absorption capacity. Unlike activated carbon, where you only have the surface for absorption, we can get in between the layers here with the 2D materials. And then our energy consumption is about 10 times less than compared to activated carbon. So we're 10 times more energy efficient. And if you were to synthesize ammonia from the fossil fuels, we're actually the amount of ammonia we can recover would reduce the CO2 emissions by a factor of 20 for the same amount of ammonia. Right. So we did do some benchmarking, say, well, why not just use graphene? Graphene has been used in FE-CDI. Their absorption capacity is much lower when looking at the same salt. And then graphene, if you've ever worked with it, it's hard to functionalize and keep stable in water, maintain its conductivity. And especially in salt water, we actually use salt water to crash graphene flakes out and collect them for using to create graphene papers for our ink synthesis. So overall, I think the MXenes show a lot of promise here, not just for ammonia recovery and remediation. We're also working on carbonate removal and other ions of interest using this FE-CDI cell. So I'll move now into, let me see how much time I have. Some of the tissue engineering work quickly, and then I'll close out with the MOCVD. So in this work, this was actually coming out of my NSF Career Award, where I proposed integrating 2D materials into the tissue engineering cycle to address musculoskeletal disorders such as osteoarthritis, volumetric muscle loss, by being able to look at new modalities for stimulating stem cells down different differentiation pathways. And the way this would integrate to the tissue engineering cycle, you have your patient that has some disorder or some ailment that you want to address. You can harvest their stem cells through bone marrow or other tissues, purify them, and these are well-established techniques. And then you would take those stem cells and seed them onto a biomaterial scaffold and induce differentiation using different biochemical cues. And then that would grow out into the tissue engineered graft, which is then genetically matched to the patient. So when you reimplant the tissue into the patient, the chance of rejection is very low compared to organ donation or some other tissue donation, right? And so we're integrating here by swapping out the biomaterial. And I think the role of 2D here can be that we can apply electrical signals to the stem cell and trigger biophysical signals through the transmembrane voltage, pH gradients, ion flux, ion concentrations at the cell material interface, which would then enable electrophoretic movement of different ions through the voltage-gated ion channels in the cell membrane and impact the genetic pathways, right? So for this, we turned to graphene and a 3D version of graphene known as graphene foam. We can synthesize this using standard chemical vapor deposition techniques with methane as our source on a transition metal foam substrate. We're using nickel foam in this case. So we do our standard growth about 1,000 degrees Celsius under methane and hydrogen. Once we have the graphite, it's largely graphitic foam with some tiny regions of graphene when you do the Raman analysis, but we call it graphene foam because that's what the original paper, the primary source, called it. So we then coat that with PMMA, use hydrochloric acid to etch away the nickel, and then we're left with this freestanding carbon foam, right? Graphitic and graphene foam. The pores here are large. They're on the hundreds of micron scale, which is good for nutrient diffusion into the tissue and waste removal as well. And then the cells are on this electrically conductive scaffold, right? So we've done some work in the past where we were able to seed this foam with C2C12. It's a pluripotent cell line that can go down muscle and bone pathway, as well as ATDC5s, also a murine line that can go down chondrogenic pathway. And we characterize the functionality through electrical stimulus and mechanical testing, right? But for this work, one of the things we noticed when we put these cells on graphene foam is black, right? It's really hard to get visible light to shine through the entire scaffold. And most of the cell morphology is typically characterized with fluorescence microscopy in the visible range, right? So you can see that here, we did some fluorescence staining of our cells, but we can only get down to about 50 micron depth into that foam. And these are about 1.5 millimeters thick. So my student, Monet Sawyer, developed a staining technique where you can actually add a gold nanoparticle on top of the fluorophore and attach it to the cell wall and use micro CT to look at the distribution of the cells throughout the 3D scaffold, right? And what we noticed is that in our standard culture techniques, most of the cell density was along the edge of the graphene foam and on the surface. We weren't getting good penetration into the cell, into the scaffold itself. So we decided to 3D print our own cell culture vessel, which would hold the graphene foam under the cell culture media, just kind of submerge it. And then we added these electrical feed-throughs so we can put electrical contact onto the foam. You can see some of the waveforms we ran through the foam, just showing that we can do different amplitudes and retain the waveform fidelity in this 3D printed structure. It's also scalable, right? It's just using standard SLA printing of a biomed clear resin, and we can scale up to standard tissue culture plates for kind of high throughput analysis. So here's kind of some of the key takeaways. You can see here just using commercial cultureware, the CC. We're looking at different micro CT at different magnifications. And the green is the cells, right? And then this ESC is our custom chamber. And so immediately, without electrical stimulus, just submerging the graphene foam in the cell culture media, you can see that we increase the penetration of the cells throughout the graphene foam scaffold. So this is top view, and then this is side view through the center of that graphene foam. And so we get much a 2x increase in cell volume under this chamber, but a 13x increase in cell conductivity, which is important for cell-cell communication as things start to differentiate, right? So just by holding the foam, we were able to get much better results. And then we decided to apply electrical signals, 0, 20 millivolts, and 40 and 60 millivolt peak to peak during the cell culture. And so we did this for 5 minutes a day over 7 days and cultured out for another 7 days. So 14 days total of cell culture for ATDC5s, and looked at the dynamic mechanical response for the grown tissue, right? And what we noticed is that the 60 millivolt peak to peak samples showed a 25% increase in equilibrium modulus, right? So that's this plot here. It wasn't really significant when you look at the statistics, but it's still an increase. But really what we did is we then went back to a paper we published in 2018, and we noticed that for the equilibrium and dynamic modulus, where we didn't submerge those ATDC5s and graphene foam in the cell culture environment and they had no electrical stimulus, the equilibrium modulus was only about 8 kilopascals, right? So we're about a factor of 3 better on that. And the dynamic modulus in that was only about 29 kilopascals. So we're about a factor of 3 improvement there as well with the electrical stimulus. But really for cartilage, one of the key things is energy dissipation, right? How well can the cartilage cushion the forces as you walk for your knees, for example, or your hips? And so when we look at the hysteresis under these different curves for the stress strain curves and look at the steady state energy dissipation, here we do see significant results of about 65% increase in the 60 millivolt peak to peak samples for this setup, right? And this paper has been published, so the details are there, but we really attribute it to an increase in collagen 2 deposition. So that's that extracellular matrix, which gives the tissue its kind of structure. So that's one of the key things, as well as the proliferation under electrical stimulus. And so if you're interested in this, happy to send you the paper. You can QR code scan it here. I will say, we do have mass spec data. So we have the genomics and proteomics on these samples, which we're still analyzing, but it does look like we're impacting different cell signaling pathways as well with the electrical stimulus. All right, so coming to the end here, I'll go through this fairly quickly, but just to highlight, this has all been kind of top down on the TMDs and MXenes, but we are moving into some of the bottom up growth of wafer scale TMDs, right, which can have applications in microelectronics and optoelectronics. For this group, if you're not familiar with the bottom up synthesis of 2D materials, there are several competing techniques. We have atomic layer deposition, which is driven by kind of the surface chemistry and the chemical reactions to grow your layer. Very fine precision, can be slow at times, but very good selectivity and very fine control of the layer growth, right? And it is fab compatible. One of the key things with ALD is conformal, right, over high aspect ratios, where ALD coming out. But if you're looking at 2D materials, most of these are low crystallinity, right? MBE, Stephanie don't want to say anything wrong here, but MBE can give you exceptional layers, excellent interface control, wide temperature range, but it can be challenging to get selective growth, and can be slower as compared to other techniques like MOCVD. Hope that's fair, right? And MOCVD is by far the best technique out of all of these, in some people's opinion. But of course, like the printers, the different tools have different advantages, pros and cons, right? It can give you large grain size, fast growth temperatures, but one of the downsides is you can incorporate carbon or contaminants from your precursors into the film, so you may not have as good of interfaces or crystalline quality as compared to something that uses pure elements like MBE, right? So our tool here at Boise State was qualified this February. We purchased the Axtron 2D close couple shower head. You can see how it's configured here, but we have 5 process gases: hydrogen, methane for graphene growth, transition metal carbide growth, hydrogen sulfide, hydrogen selenide, and ammonia for gallium nitride growth, right? We have 12 metal organic sources. Right now we have triethyl boron, tungsten and molycarbonyl, trimethyl aluminum, and trimethyl gallium on the tool with room for expansion. Each of these channels has a Epson 5 gas concentration controller. It is equipped with an Argus pyrometer to do kind of the multi-channel thermal mapping, look at the wafer surface temperature with the latex FE-TT as well. And so we can control the process based on gas concentrations and the wafer temperature, right? We do have photoreflectance, I should say, sorry. The FE-TT can also measure the photoreflectance of the sample for controlling the process. The advantage of the closed couple shower head compared to the horizontal reactor is that the precursors are kept cool and separate until they get inserted into the chamber, right? So the gases are injected and the precursors are injected at about 5 millimeters above the wafer surface, and so they don't see each other until that point, which can improve kind of your control of the reaction. And then our susceptor does rotate up to 100 RPM, and so that can ensure good uniformity as well. We do not have a tunable gap on our system. Ours is fixed. Another advantage is that we have the 3x2 reactor, but Axtron has engineered this in such a way that you can just scale in theory, scale all your precursor and gas flows by these different scaling factors to go from the 3x2 all the way up to the 300 millimeter tool set that they have, for example, at IMEC. So this is what a typical process would look like in terms of data we're collecting out. So you see here the temperature monitoring and then the photoreflectance change. And so you can see we do a substrate anneal based on Professor Redwing's work of H2S. And so we can anneal at high temperature, reconstruct the sapphire surface. This is just a hydrogen anneal. I'll show you the H2S anneal shortly. Then we can drop the temperature, do our nucleation, keep the temperature constant for our growth while the photoreflectance increases. And at some photoreflectance change, which you calibrate for your system, you can get the full monolayer coalescence, right? And so here's just an example of our substrate preparation and nucleation. So here's the hydrogen pre-anneal and the hydrogen plus hydrogen sulfide pre-anneal. So we see a nice reconstruction of the sapphire surface, getting the nice kind of aligned terraces that we saw in Professor Redwing's work. And then we can switch the nucleation, and you can see the small triangles nucleate at the edge. This is WS2. And so we're nucleating at 900 degrees Celsius under tungsten carbonyl and hydrogen sulfide flow. And we do see some good alignment, suggesting we might get good epitaxy in the growth. So here's the evolution of the growth, just looking at different SEM images from 0.5 to 2.5 or 3% photoreflectance change. So we do get fully coalesced WS2 over our 50 millimeter sapphire wafers, but we do end up with about 18 to 20% bilayer coverage. And that's just through image analysis, looking at the image contrast, right? And so looking at the uniformity across the wafer, you can see here the different points where we looked at the Raman spectra. And so we're overlaying 50 Raman spectra here. So there's not a lot of variability in the Raman spectra. There is some, but it shows pretty good uniformity across the wafer surface. And then this is the same Raman scheme, but done on a process that was run 2 weeks later. And so we do see a bit of a spread in the ratio of the LA mode to, I think it's the A prime mode, right, which is an indicator of defect density. But overall, the process looks pretty uniform, even weeks apart, right? The recipe is pretty constant. So we're still improving our growth recipe, trying to get lower monolayer coverage. I will say we did do GI-XRD. Those films are bidirectional, so it's not really epitaxial, but we are still improving our process. And one of the other things we've done recently is develop our own photoresist, so we can do photolithography directly on sapphire. We have a contact aligner here at Boise State, and so when we do contact alignment through transparent substrates, the UV will reflect off the aligner, re-expose your photoresist, and you don't get the good resolution that you're targeting. So we have a UV blocking layer in our liftoff resist now that allows us to pattern these TMD films directly on sapphire. May not be great for device applications because that sapphire really dopes the film. You can't get good offstate leakage, but for maybe optoelectronic devices or other types of devices patterned directly on sapphire, this approach will work quite well. So with that, hope I've just kind of introduced you to some of the applications we're using here at Boise State for 2D materials. And I'll thank the team, Estrada for the supercapacitors, Ajay on the Tang, Naksh on the water, Monet on tissue engineering. Michael actually learned MOCVD from Joan at the 2DCC, and then went out to Axtron to learn the tool the following summer. Estrada was out there for the CVT, growing crystals that of TMDs that we're now using for ink synthesis as well. So with that, also thank the funding agencies, 2DCC for the participation of the RSVP program with our students, and then NextFlex and AFRL for the research support. So thank you.
All right, hopefully the owl doesn't script the audio too much, so we have time for a few questions. So if you're online and you have a question, you can unmute yourself and ask it, or put it in the chat, and I will read it out, or we have also people in person can ask questions. Yeah, go ahead.
Yeah, so thank you, Dr. David, for your absolute insight of these applications and TMD growth using the MOCVD. So actually, I have two quick questions. One is I saw you used hydrogen sulfide in the pre-growth anneal, and you show the nucleations. Did you get any extra data about how that affected the epitaxial, and also that's the overall properties of the tungsten sulfide film. Another question is about the new Estrada system. Can you share your some insight about how this system goes, and then what is the key takeaways about the using the system and the process for growth the TMDs? Thank you.
Yes, yeah. So first question, right? The quality of the film. I think our growth temperature initially was a bit high, right? So we've gone back to kind of just look at the evolution of the sapphire surface under different hydrogen sulfide flows with and without hydrogen present as well, to look at how that surface evolves as a function of temperature. And I say that because I think the alignment you get with the hydrogen sulfide anneal, pre-anneal, can go away over time and at higher temperature during the growth phase, right? And during the growth, I think that impacted us because we actually ended up, when we looked at the GI-XRD data with Air Force Research Labs, we had a peak at 11 degrees and one at 2.5 degrees. And we didn't see this in the work coming out of Penn State, right? So we have a bidirectional film that does not necessarily look epitaxial. So that's one thing. We have not measured any physical properties of the film. I mean, we could easily do optical transmission and things like that, but we haven't done mobility. We're focused now on improving the growth a little bit before going into the device applications. Regarding the use of the tool, I think probably hydrogen flows, things that caught us by surprise, were the amount of nitrogen and hydrogen that were required. one, to dry the lines to the critical dew point before you're able to qualify the system. At one point, we calculated we'd have to swap out 50 hydrogen cylinders to meet the flows. And when you break that line, you might introduce more, luckily we're pretty dry here in Idaho. You're not as dry in State College. So if you break that hydrogen line, you might reduce your dew point again and then have to start over. So really understanding how much nitrogen you need and how much hydrogen you need is key. We also saw that we didn't split our auxiliary nitrogen from our process nitrogen. So everything now runs through the nitrogen filter. And we're using really like six nines of nitrogen to run the pneumatic valves, which is a bit of a waste, right? So that's something to be aware of. And then the other thing I would say is it is not straightforward to translate recipes from a horizontal reactor to the shower head, right? And then the role of nitrogen is also something we're trying to understand, because our process gas is nitrogen. We're not flowing in all hydrogen, which I think Michael was doing when he was at 2DCC, right? So there's a lot of nuance here, and luckily you have one of the world experts. You guys will be quick when your tool comes up, but it won't be a straight translation of previously developed recipes. Does that answer your questions?
All right. Are there other questions online or in person?
I guess I could ask a question. So it looked like your uniformity was good across like the 3 2-inch wafers. Did you have to do any tweaking of the shower head flows to optimize uniformity?
No, I would say no. I think
Okay.
we were equally bad when we had what we did see was the chalcogen metal ratio plays a significant role in the quality of the film, of course, right? But uniformity was equally bad across the wafer or equally good when we finally optimized the recipe.
Okay.
And one thing also, we did get all the way out to the wafer edge, I think within 1 millimeter, where we had really good quality film before we started to see less coalescence at the wafer edge.
Yeah. The results look really nice.
Oh, thank you. Yeah, we actually have better, but I can't share that yet.
Yeah.
All right. Any last questions in person or online? All right. If not, let's thank Professor Estrada again for an excellent talk.
Yeah, sorry.
All right. Thank you
Thanks,
so
everyone.
much.
Thanks, Joan. Yeah, and Joan,
See you.
if you want to catch up more on the Actron anytime, we can set up a call with Michael.
Yep. Definitely. I'm sure we'll be in touch.
Okay, thanks. Bye.
Bye, everyone.